Hello and welcome to SLOconf. My name is Eric Moore. I'm going to be talking about confident rare SLOs, how to mostly monitor SLOs which are composed of rare events. Things like errors when you've got a low QPS service. So as an example, suppose we've got a program that just returns errors one time out of 1,000 randomly. So pretend that there's no external errors, all the errors live inside the program, just conceptually speaking, and we're calculating a fraction of errors. And we're going to set an SLO. In this case, 3 nines. What are the actual results we're going to get? So theoretically speaking, if you're doing measuring for an hour and you've got a 1 QPS service, you're doing 1 QPS, you've got 3,600 requests. On average, you'll see 3.6 errors. However, you're not going to see 3.6 errors every hour because you can only get 3 or 4 or an integer number of errors or integers. You're going to get results that look like this. The black bars are for 1 QPS, and it's going to vary a lot. What you would probably do when trying to monitor this is set your error budget more around 2 out of 1,000, because you don't want to get alerted for just 1, because as you can see, there's a very significant fraction of results over 0.15 or 1.5 errors out of 1,000. So you'd normally set the error budget if you got 1 QPS around 2 out of 1,000, but that's way too high for the 10 QPS service, which is always going to reserve results under about 1.5 out of 1,000, and far, far too high for the 100 QPS service, which is going to be operating in a much narrower range. We're going to be talking about the statistics of that. Quick 30-second review. This is the normal distribution. It's a Gaussian curve. The width is called the standard deviation. About 2/3 of the time you'll be within 1 standard deviation of the mean, 95% of the time within 2, 97.5% of the time will be more than 97% of the time be more than the mean minus 2 standard deviations. The distribution that governs these sorts of events where something can happen or not some number of times per second is the binomial distribution. And for large N, where you've got a lot of requests, it looks a lot like a Gaussian, but at the lower end, it does not. There's some math. The key features I want you to take from this one are just that the mean is just the number of trials times the probability of a trial. So we got the 3.6 before. The variance is, if p is much smaller than 1, if we're talking about 1 in 1,000 errors, the variance is equal roughly to the mean. And the variance is the square of the standard deviation. So that's going to give you some idea of the width of your distribution. So something is rare if it occurs 400 times or less in a given interval. This is my rule of thumb. Basically here, the standard deviation is about 20 on this. So you're going to typically get 95% of the time, if the average is 400, you're going to get between 360 and 440 or plus or minus 10%. If you got more than 10% variation from interval to interval, that's a lot and you should try to account for it. We're going to try a better way than just sort of eyeballing where you typically come in or where you very rarely go above, and try to use statistics here. So the statistics we're using are the confidence interval. The confidence interval is essentially just taking a set of measurements that we took and saying what is the plausible range that the underlying probability could be. So before we're going, if we know that there's a 1 in 1,000 chance of this thing happening each time out of 3,600 trials, what's the number of times it'll happen? This is, out of 3,600 trials, it happened 4 times. What are the lowest and highest values that the underlying probability could be. We're going to simply use the lowest probability that it could be. We're going to use the lower bound of our confidence interval as our error rate, as the percentage of errors we're getting. This allows us to, be confident that whatever the true error rate, we know it's higher than that. So if we're using the lower bound and we compare that to our target of 1 out of 1,000, if we're 95% confident it's above 1 out of 1,000, then we're good. If it could be 1 out of 1,000 or it could be less, we don't typically want to alert. There's some formulas. I pulled these images off Wikipedia. There's a lot of math here. If you really need it, go to Wikipedia. The article's name is Binomial Confidence Intervals or something like that. The key thing that I want you to take away is what I said before, that if P is close to 0, much smaller than 1, 1 minus P is about 1, we can get these very simplified distributions for the normal and Agresti-Cool, where we essentially just either take off the square root of the number of errors, or twice the number of square root of the errors of Z. Z is the measure of how many standard deviations we're interested in. And for Agresti-Cool, we just replace N by, or the number of errors by the errors plus Z squared over 2, and the number of trials by N plus Z squared. If Z is 2, this is just 2 and 4 respectively. How do these work in practice? So here we've normalized everything by the number of errors. We're doing, this is P equals 0.001. P is very, very much smaller than 1. The Wilson interval, that's statistically the most valid. It's generally got the best results. The statisticians like it. It's very complicated, but it's good. And it's going to give you the highest values at very low numbers of errors. The Agresti intervals and the simplified Agresti are right on top of one another, and by 10 errors are virtually identical to Wilson. Can't get any better than that. And the Gaussian, or the normal approximation, significantly worse, but by 100 errors, it's well in there. So depending on how much math you want to do, you can get better or worse results. If you are running something closer to a 9.5s than a 5.9s SLO, and P is closer to 0.5, which is sort of the worst case for these things, you'll see that in this graph, the simplified versions are not working as well. They're well below the complex versions. In those cases, you want to do that. But the Agresti falls right on top of the Wilson limit at this limit. And in any case, by 10, almost the complex formulas are working. And by 100, you can do almost anything. And 100 errors, as long as you're doing some kind of statistical correction here, you're going to get good results. And by 10, you can almost always use the Agresti or the simplified Agresti if you have in the right range. So what do? So you're going to want to replace the error rate you're using in your SLO computations, your burn rates, whatever, by the lower bound of your confidence interval. What confidence intervals do you want to use? If you need to impress the data scientists or other statisticians, if you really want to be mathematically very sound, use the Wilson interval. Or if you really, really, for whatever reason, need to be able to pick up on small deviations from your SLO, even at really low error counts, 1 to 10 errors. So, I mean, at 1 QPS, that's still a 2-hour, it's a 2-hour, 1 to 3 hour window. Then, but that's for very small deviations. If you're going in a 1-hour window, obviously, if your service is down completely, you're running 100%. None of these are going to make much of a difference at all. So then If you're really lazy and your probabilities are, you're got 9.5 SLO, you're going to use the Gaussian approximation. I've sort of tried to put that there. That's the easiest way you would program it into whatever monitoring system you're using. If your probabilities are more like 2.9s or you're 2.9 or better SLO you're comparing to, you can use the simplified Gaussian. You just subtract the square root of the number of errors, twice the square root of the number of errors to get the 95% confidence limits, or 97% because we're okay. If you want to be a little bit fancier, you can use the agreste-cool. If you're using z equals 2, if you're using the 95% confidence level, add 2 errors, add 4 to the total number, and then plug it back into the simplified Gaussian. So e plus 2 minus the square root of blah, blah, blah. And the simplified agreste-cool, again, adding 2 and 4 to the errors and the total number of attempts, respectively, gives you this very nice little formula. Honestly, unless you're in a really weird case, I almost always suggest using the simplified agreste-cool interval. Just add 2 errors, add 2 successes, or add 4 to the total denominator, subtract square root, twice the square root of your adjusted number of errors, you're golden. It's easy to plug this into any, say, into Noble Nine's stuff, and you can then evaluate all of these over multiple windows, even if you want. So if you are looking at a 1 hour, a 3 hour, a 10-hour window, you can, the bigger windows, you'll have a smaller correction because n's going to be bigger, and you're going to get better windows. You can simultaneously monitor using multiple windows to try to get the best result. And if you just simply use this simplified agreste-cool, you'll have excellent results as long as you're not going on 9.5s or you're doing like a 1.9 or better SLO, you'll probably be fine. The last bit of statistics I just want to throw at you in this little talk. If you don't have a denominator, if you don't have a number of trials, you've just got a number of times something happened, that's the Poisson distribution. It looks a lot like the binomial distribution. It is the limiting case of the binomial distribution. And again, you're going to have the result where the variance and the mean are the same. So you can just you can estimate the standard deviation by taking the square root of the mean. So if on average, this is good for measuring, say, incidents per quarter. If you've got 9 incidents per quarter on average, in any given quarter, the standard deviation is going to be square root of 9, 3. So you're going to have plus or minus 6. So in any given quarter, you have between 3 and 15. And so then if you're trying to keep your average number of incidents down to 9 per quarter, you really shouldn't do anything until you got above 15. That's just a bit of helpful statistics about how to think about these kinds of things. Hope this was helpful. I should be able to answer questions. Good luck.